Good evening and welcome to this video for integration by partial fractions. Now this concept is one that is commonly tested on the NCEA scholarship examination for calculus. So for anyone that's willing to do the calculus exam at the end of the year, this is a very crucial skill to be able to have, and it does come up, there is a possibility that it will come up with the exam, so it's a handy tool to have in your exam. So what is integration by partial fractions? So integration by partial fractions involves splitting a complex fraction into two smaller parts to be easier to integrate. So for example, if you have one big fraction, you can actually split it up into two smaller fractions given the correct circumstances. Like for example, if you remember in your level 2 exams, you're usually asked to join two simple fractions into one more complex fraction. Well, in this case, we're going to be going the opposite way. So we're going to be making a complex fraction into two simple fractions. So let's say we have a over bx plus c plus d over ex plus f. We can actually rewrite that as a bigger fraction by doing a cross multiplication. So we can actually get d times bx plus c, that's just cross multiplication, plus a times ex plus f, all over the two denominators times together, which is bx plus c times ex plus f. So similarly, we can use two small angles to make one bigger fractions. So similarly, we can actually take one of these bigger fractions, one of these complex fractions, and go backwards to make it two easier fractions. So level 2 question, like I was just saying, is joining two simple fractions to make a big fraction, so we'll just be going the opposite way. Alright, so the reason we do this is that if integrating two simple fractions is a lot easier than integrating one complex fractions. So if you look on the left on the example there, so we can integrate a over bx plus c very easily. So if you know your ln rules, you can just say that the integral is a over b ln of bx plus c. So that's a very easy integral you can do. Same with d over ex plus f. You can say that the integral is d over e ln of ex plus f. That's your simple ln rules there. But if you look on the fraction, the one complex fraction on the right, that will be much harder to integrate because there's a lot more terms you have to factor in. So basically splitting it up will make it easier for us to integrate. So the process of splitting the fractions. So in partial fractions, you split the denominator only if it's the product of functions with respect to the variable that you're integrating. So for example, if you're integrating with respect to x, and you have two functions that multiply together, that they're both with the variable x, then you can split them up. So this is very similar to the product rule. So if you have two functions that are multiplied that are of the same variable, you can split it up, okay? For example, if we have f of x equals to 3 over 3x plus 3 times 6x minus 1, as you can see at the denominator, we have 3x plus 3, that's a function of x, and we have 6x minus 1, that's also a function of x. So this becomes f of x equals to a over 3x plus 3 plus b over 6x minus 1. We actually don't know at this stage what a and b is. We actually have to rejoin the fractions and make it equal to 3 in order to find what our a and b values are. So to find the a and b values in this case, we're just going to treat this as a question that asking us to join the two fractions again. So we're going to join it back by cross multiplying. So we'll get a times 6x minus 1 plus b times 3x plus 3, and that should equal to whatever's on the top, the numerator of the original fraction we had. So that's equal to 3. So we can actually make simultaneous equations here. So we can say that 6ax minus a, if we expand the brackets, plus 3bx plus 3, and that equals to 3 plus 0x. There is no x, therefore it's just 0x. So therefore all the x terms should add to 0 because it's 0x, and all the terms without x should be adding to 3. Therefore you can say in this case that 6a plus 3b equals to 0, negative a plus 3b equals to 3, and in this case you can just plug and chug it into your calculator in order to find your a and b values. Alright, so that's for a second degree polynomial. That's for x squared. So what is happening with a higher degree polynomial? So last example only considered a quadratic in denominator because we had linear times linear that gives us a quadratic. So what happens in a third degree polynomial? What about a fourth degree? As you can see here, there's an example of a third degree polynomial at the bottom. So we have three linear functions times together. That's going to give us a cubic. So in this case, we're going to have to be splitting it one by one. So we're going to take one of these linear functions, and we're going to be splitting it up from the rest. So we're going to say that a over that linear function plus bx plus c over the quadratic. Okay. So remember, whatever's on your top, so that's your a, your b, and your c. So whatever's on the top has to be 1 degree less on whatever's on the denominator. So for example, 2x minus 2, that is degree 1. It's just x by itself. 1 degree less is just no degree of x. So therefore, you can just have an a constant. However, for x minus 9 times 3x plus 1, if you multiply that together, you'll get a quadratic. And that quadratic, it's x squared, so whatever's on the top has to be 1 degree less. That's 1 degree, so 1 degree would mean a linear, which is bx plus c. So that means it has to be a bx plus c at the top. Similarly, if we had a cubic at the bottom, we would need to have ax squared plus bx plus c. We need to have a second quadratic on the numerator. So always 1 degree less on the numerator. Alright, so that's what I just said. So in this case, we will have, if we wanted to solve for a, b, and c, we will say that cross multiply once again, so join the two fractions to cross multiply, and we should solve the simultaneous equations for, so we should solve the simultaneous equations. So we're going to make equal to whatever's on the top, which is 3x plus 3, and we could solve for a, b, and c. But we won't do that for now. If it's just an example, we'll have some example questions coming up soon. Alright, so here's our first example. So this is an easy example. Here we have integral of 3x minus 3 all over 2x plus 2 times of 5x minus 1 dx. Alright, so in this case, we do meet the requirements for partial fractions because we have two functions of x times together, two linear functions. We're going to be splitting it up. So we're going to say that a over 2x plus 2 plus b over 5x minus 1, that equals to 3x minus 3 over 2x minus 2 times 3x plus 1, because we're not changing the question. Alright, so now we're coming back to our general idea. We're going to be cross multiplying and solve for a and b via simultaneous equations. So if you cross multiply, you should get that 5ax minus a plus 2bx plus 2b equals to whatever's on the top to begin with, which is 3x minus 3. So x is a term and negative 3 is a term. So all our x terms on the left-hand side equals to our 3. And all the non-x terms on the left-hand side equals to our negative 3. Okay, so we join, in algebra, we join like terms, remember? So we will have 5a plus 2b equals to 3. That's our 5ax plus 2bx equals to 3x. And we have negative a plus 2b equals to negative 3. That's our negative a plus 2b. At this point, okay, you have a graphics calculator. So in the exam, don't waste time. You have a graphics calculator, you might as well use it. So if you plug and chug those numbers into your graphics calculator, you can instantly get that your a is 1, your b is negative 1. The next step into this question is to rewrite the function as a and integrate. So rewrite the new integral you have and integrate both terms separately, because now you're going to have two terms, something plus something else. We're going to integrate it separately. So now we'll have an integral of 1 over 2x plus 2 minus 1 over 5x minus 1. And how did I get that? I get that by plugging a and b back into my formula, because we found a and we found b. So in this case, we can just apply our basic ln rules, and that should give us half ln 2x plus 2 minus 1/5 of ln of 5x minus 1. And don't forget the plus c at the end, plus the constant of integration. And that's it. That's your final answer for this question. Example number 2. So integrate f dash of x equals to 1 over x minus 1 times x plus 2. So another easy question here, we can just split the fractions up and we get our a and our b. Find our a and our b, and we can integrate. So follow the steps, split the fraction. So we have a over x minus 1 plus b over x plus 2, and that equals to 1 over x minus 1 times x plus 2. Once again, we're going to apply our same rules to cross multiply, solving for a and solving for b. So we'll get that a times x plus 2 plus b times of x minus 1, and that equals to 1 plus of 0x, because 1 by itself is just plus 0x. They don't write the plus 0x, but it just means plus 0x. So if we will see that a plus b equals 0, 2a minus b equals 1. Once again, chuck into a graphics calculator, should get that a is 1/3 and b is negative 1/3. So now we're just going to plug those numbers back as our a and our b values in our equation. We're going to rewrite our integral. So if we rewrite our integral, we'll get f of x f of x equals to the integral of 1 over 3 times x minus 1 minus 1 over 3 times x plus 2 dx. Okay, so now we can just once again apply our basic ln rules here. So we can just say our f of x equals to 1/3 of ln of x minus 1 minus 1/3 of ln of x plus 2, and we're going to add the constant integration at the end. Right, so example 3, we're going to step it up a little bit. We're going to make it a cubic at the bottom, a bit harder than the last few questions. So we're going to say, we're going to ask ourselves, what is the integral of 1 over x minus 1 times of x plus 2 times of 4x plus 2? If we follow the same steps, we're going to isolate one of these linear functions by itself, and we're going to keep a quadratic on by itself as well. So we're going to split it up into two different terms. So we're going to say we can split the fraction to a quadratic and then a linear. So a over x minus 1, it doesn't have to be x minus 1, it could be a over x plus 2, it could be a over 4x plus 2, okay, just choose one of the three and use it as a over that linear function. So it doesn't have to be x minus 1, okay, it could be any of those, it could be a over x plus 2, a over 4x plus 2, but for the specific walkthrough, I chose a over x minus 1. Remember, we have a quadratic as our second term in the denominator. Therefore, on our numerator, we need to have 1 degree less, which is a linear bx plus c. We do not know these values. And that equals to 0x squared plus 0x plus 1. So notice how I have plus 0x squared on the right-hand side. So we know that the the highest power on the denominator on the left-hand side. So the highest power is x squared. So therefore, on the right-hand side, we also have to have x squared as our highest power. So we're going to have x squared on the right-hand side, x squared on the left-hand side, okay? So that will work with anything. So if we had a third term, so we had a cubic at the denominator, we had 0, we would have something x cubed plus something x squared plus something x plus something, okay? So it just goes on as we have adding more powers of x. So now we're going to solve for a, b, and c, and once again, it's the exact same process. We're going to cross multiply, and we're going to make our three simultaneous equations. So now we have a times of x plus 2 times of 4x plus 2 plus bx plus c times x minus 1. That equals 0x squared plus 0x plus 1. So if we expand everything, we should get that 4ax squared plus 10ax plus 4a plus bx squared minus bx plus cx minus c, that equals 0x squared plus 0x plus 1. So now we can go once again, the like terms are equal to each other. So all the x squareds added together equals to our something x squared on the right. All our x's added together equals to our something x on the right. And all our non-x's will add to something without the x on the right. We get our equations 4a plus b equals to 0. 10a minus b plus of c equals to 0. We'll have 4a minus c equals to 1. And we're going to chuck that into our graphics calculator. So this will be three unknown variables. So we get a equals to 1 over 18, b equals to negative 2 over 9, c equals to negative 7 over 9. So now we're going to rewrite our integral. So we're going to rewrite our integral, that is 1 over 18 times x minus 1 plus negative 2 over 9x minus 7 over 9 over x plus 2 times 4x plus 2. So now we're not quite done. We're going to have to split up the fraction again. So now we have our quadratic equation as our second term. We're going to split it up into two linear fractions. Okay. So once again, this is just doing what we did in example 1 and 2. So going back to example 1 and 2, it's the exact same thing now. Alright, so ignore example. We're still at example 3. So ignore the first part. We're ready to integrate it. So now we need to split the fraction again. So that's the exact same thing we did in question 2 and question 1. So because we've already used a, b, c, and d, I'm going to choose the next variable, which is e and f. So we're going to follow the exact same process. Cross multiply. We get our two equations. 4ex plus 2e plus fx plus 2f equals to negative 2 over 9x minus 7 over 9. Into your graphics calculator gives you e equals to 1 over 18, f equals to negative 4 over 9. And now you rewrite your integral again. So now you have your e and your f. You're going to rewrite your integral. You will get the this big chunk. So we're just going to use our ln of rules. ln rules will give us our final answer, 1 over 18 ln x minus 1 plus 1 over 18 ln of x plus 2 minus 1 over 9 ln of 4x plus 2 plus the constant of integration plus c. Right, so let's make it even harder now. So let's go to example number 4. So now I have to integrate f dash of x equals to 3x squared plus 6x plus 2 all over 2x plus 3 times of x plus 1 squared. Alright, so this question is very similar to the last question, except notice that I actually have x plus 1 squared, which is x plus 1 times x plus 1. So I won't explain what that means right now. We'll just continue with the question, and when we get there, I'll explain what that actually means. So we're going to split up our fraction. Okay, we're going to split it up to our linear and our quadratic. So in this case, it's best to isolate the 2x plus 3 away from the x plus 1 squared. So for example, if you have 2x plus 2 squared and something else, it's best to isolate the linear one from the quadratic. So in this case, x plus 1 squared is a quadratic. We're going to isolate that from the linear one, which is 2x plus 3. We're going to get a over 2x plus 3 plus bx plus c all over, it's not all over x plus 1 squared equals to 3x squared plus 6x plus 2. Now in this case, we're going to carry out the exact same process. We're going to do our cross multiplication and use our simultaneous equations to solve for a, b, and c. Right, so ax squared plus 2ax plus a, so that's a times of x plus 1 squared, plus 2bx squared plus 2cx plus 3bx plus 3c equals to 3x squared plus 6x plus 2. And once you solve all your equations, all your simultaneous equations, you get a is -1, b is 2, c is 1. So now we're going to rewrite the integral. So rewrite the integral, we're going to get f dash of x equals to -1 over 2x plus 3 plus 2x plus 1 over x plus 1 squared. Right, so some of you guys might be thinking, okay, so now the next step would be to separate our x plus 1, and we're going to have x plus 1 and x plus 1. The problem with that is that actually doesn't work well, okay? So when you have an x plus 1 squared, and you try to split it into two x plus 1s, it never works. So in this case, you actually have to think of another way in order to integrate 2x plus 1 over x plus 1 squared. So whenever you're in this type of situation and you can't use partial fractions, in this case, you have to ask yourself, wouldn't it be nice? So wouldn't it be nice if this happened, okay? So notice that the denominator is x plus 1 squared. The derivative of x plus 1 squared, that is 2x plus 2. So the derivative of x plus 1 squared is 2x plus 2. So wouldn't it be nice? Wouldn't it be nice? Remember, ask yourself that question. Wouldn't it be nice if the top was 2x plus 2? Because if the top was 2x plus 2, then we could just say it's ln of x plus 1 squared. Because ln of x plus 1 squared, that is, if we find the derivative, we'll just get 2x plus 2 over x plus 1 squared. So that would be perfect. That would be so nice, wouldn't it? So in this case, we have to make it reality, okay? So in this case, we can stop dreaming and we can actually make it happen. So how do we make that happen? So 2x plus 1, okay? So first things first, remember to never change the question. So the question has to remain the same no matter what you're doing. So whatever you're adding has to be whatever you're subtracting. So we can change 2x plus 1 to 2x plus 2 by adding 1. By adding 1, we need to subtract 1 over 1 plus 1, x plus 1 squared. So this can be a totally separate term. So if we see what I did here, so we have our -1 over 2x plus 3, we leave that by itself. So now we're going to add 1 over x plus 1 squared into that fraction. So we get 2x plus 1 over x plus 1 squared. Whatever we add is whatever we take away. So we have to minus 1 over x plus 1 squared. So now what we're left with is actually, all we need to integrate, so we know how to integrate 2x plus 2 over x plus 1 squared, that's very easy. All we need to do now is integrate 1 over x plus 1 squared, and you can use substitution for that, you can use reverse chain rule for that, okay? It's not a hard integral, so now life is easy, we can integrate the last term by using reverse chain rule or a substitution method. So at the end of the day, we get f of x equals to -1/2 of ln of 2x plus 3 plus 2 ln of x plus 1. So it should be ln of x plus 1 squared, but by using log rules, I take the squared back out into the coefficient. So I get 2 times of ln of x plus 1, that's our log rule. And if we integrate -1 over x plus 1 squared, we get plus 1 over x plus 1 plus of c, our constant of integration. And that's the answer. Alright, so we're going to look at our final example here. So this is a challenging example. So we're going to integrate f dash of x equals to 4x plus 6 over x minus 1 times x squared plus 9. So once again, we're going to split the fraction. So the linear and the quadratic needs to be separate. So we have our a over x minus 1 plus bx plus c over x squared plus 9. Because we have a quadratic, which is x squared plus 9, and we have a linear. So the linear should always be separated from the quadratic, okay? Which in this case, you would just split both of them together. So in this case, you will have this equation. So once again, cross multiply, find your a, b, and c. So in this case, you'll get, if you cross multiply, you'll get ax squared plus 9a plus bx squared plus cx minus bx minus c equals to 0x squared plus 4x plus 6. And I assume you know, by now you know how to make up your three equations and plug into your graphics calculator. You'll get a equals to 1, b is -1, and c is 3. We're going to rewrite our integral now. So rewriting our integral, we have f dash of x equals to 1 over x minus 1 plus -x plus 3 over x squared plus 9. So once again, it would be really good if we could separate this second quadratic again into two linear fractions. However, we cannot factorize x squared plus 9. Okay, no matter what you do, x squared plus 9 is non-factorizable, and that brings us a bit of trouble because we need the only way we can separate with partial fractions if we have two functions of x multiplied together. In this case, we don't. Because we can't do that, we're going to have to ask our question again. So wouldn't it be nice? Wouldn't it be nice? Okay, so we're stuck again. So x squared plus 9 can't be split into a product of two linear functions. So ask, wouldn't it be nice? So in this case, we're going to find the derivative of the denominator. So derivative of denominator is 2x. And then you look at the numerator. You see -x plus 3. Wouldn't it be nice if we just had -x there? Wouldn't it be nice? If we just had -x there, we could just say that -x is half of the derivative. So, I mean, it's negative half of the derivative. So we can just say that the derivative is -half ln of x squared plus 9. Wouldn't that be nice? Okay, so now you know what you have to do. So you have to take that 3 away. So if we take that 3 away, we're going to have to add it on back again later. So we're not going to change the question. So let's do it. Let's do it, guys. Remember, what's taken away must be given back. So we have our f dash of x equals to 1 over x minus 1. We don't touch that. So minus x plus 3. Okay, we don't want the 3 there. The 3 is annoying us. So we're going to get rid of the 3 by taking 3 away. But however, if we take 3 away, we're going to have to add it on again. So we have to plus 3 over x squared plus 9. So now we need to integrate the final term. So we know how to integrate the first term. We now know how to integrate the second term. Now we're left with the third term, the 3 over x squared plus 9. And this is a very, very challenging integral because substitution and chain rule does not work because we have an x squared at the bottom and no more x's anywhere else. So if you use the substitution, you'll get 2x that you cannot get rid of. So that's no good. So this is a classic example of a trigonometry substitution. So I want you guys to try it yourself. So I want you to use the substitution x equals to 3 tan u. And I want you to use that substitution to find out the integral. So I want you to pause the video and give that a try first. Alright, so what I have here is, so we have 3 over x squared plus 9. So if we have x equals to 3 tan of u, so x squared would be 9 tan squared of u. So that would give us integral of 3 over 9 tan squared of u plus 9. And that's still with respect to dx because we haven't changed dx to du yet. So tan squared of u plus 1, we know that's equal to secant squared u. So therefore 9 tan squared u plus 9, that equals to 9 times of secant squared u. So we can actually plug that back in. We can say that so it's the same thing as saying the integral of 3 over 9 secant squared of u, and it's still with respect to dx. So let's change the dx to du. So we're going to find the derivative. We're going to say dx over du is 3 secant squared u. Therefore, dx equals to 3 secant squared u times du. So now we have 3 times 3 secant squared u over 9 secant squared u. That's equal to 1. That equals to 1. So now we have integral of 1 du. That gives us very easy integral. That gives us u plus c. So now we're going to have to find u in terms of x. By doing that, we can rearrange the formula. So we let x equals to 3 tan of u. X over 3 equals to tan of u. Therefore, if we take the inverse of both sides, we'll get u equals to tan. Sorry, it should say u equals to inverse tan of x over 3. Therefore, f of x equals to tan inverse of x over 3 plus our constant integration. So that's our integral for 3 over x squared plus 9. So now let's finish up our question. Okay, we know how to integrate everything, so let's do it. Okay, so let's finish up our original integral. So integral of 1 over x minus 1 minus x over x squared plus 9 plus 3 over x squared plus of 9. We'll get f of x equals to ln of x minus 1. That's just basic ln rules. Minus 1/2 of ln of x squared plus of 9. Once again, that's just easy ln integral there. So plus our integral we just found, which is tan inverse of x over 3 plus of c. And that's our final answer for this question. Alright, I hope you enjoyed this video, and I hope you now know how to integrate partial fractions. And if you did like the video, please drop me a like, and I'll see you all in the next video. Thank you. Bye.